Once again, in this example, we want to know what's f of 0 and the steady state value of f, or f of infinity. So let's look at what is s times f of s as we are going through our analysis. So first, I want to show that the poles, or check if the poles, are all in the left half plane of s times f of s. So I'll use the factored form for right now. So s squared plus 3s plus 4 over s times s plus 1 quantity squared. So I will show this step by step. So I'm taking s and multiplying it by f of s. And what's going to happen is that the s out front and the s in the denominator are going to cancel. So this I can rewrite as s squared plus 3s plus 4 over just s plus 1 quantity squared. And I want to check the poles of this fraction. So notice that that s that was in the denominator went away when I multiplied by s. So looking at the denominator now, it is quadratic. I'm going to have two poles. I need to check both of them. So what are the values of s that make the denominator 0? Well, we're going to have, I'll put it in braces here, -1 and -1. So here we have repeated poles of -1 because we have that s plus 1 quantity squared. If s plus 1 were not squared in the denominator, we would have a single pole at -1, which would still satisfy the conditions to use IVT and FVT. But here we have repeated poles, -1 and -1. And there is a difference between having one pole at -1 and repeated poles at -1 further down the line. In terms of checking the poles, it turned out not to matter in this one, but we do need to be careful that we do have two poles, -1 and -1. And that's different than a pole at -1. All right, so it does pass that test for stability. All the poles are in the left half plane. So let's look at what happens to our f of 0. We'll do that one first. So what is f of 0? Well, we can use IVT now because all the poles are in the left half plane of s times f of s. So for here, I can use the limit as s goes to infinity, and that will be my f of 0. That's my initial condition of s times f of s. When I'm taking f to infinity, I like to use the non-factored version of this. So I'll write this out again longhand. So s times the non-factored version. So s squared plus 3s plus 4, and the denominator s cubed plus 2s squared plus s. Now, that s out in front, I can actually distribute, and I would, there's different ways I could do this. I could just multiply everything in the numerator by this, or I can do some canceling of the denominator like I did above. So I'm actually going to cancel things in the denominator, plus 4. So really what this is going to do is it's going to lower the degree of every s term in the denominator. And that would be one way to do this. So s squared plus 2s plus 1 is one way I can write this. Again, it would have been fine also if I just put that s in the numerator. I'm going to get the same result either way, whether I am dividing or multiplying, basically. All right, and I was a little bit lax here. This is the limit as s goes to infinity of both of these things. So I'll put that out in front here to remind myself this is what we're actually trying to do. So the limit as s goes to infinity. All right, now I can actually do that limit. I can let s go to infinity. If we look now, in the numerator, we have a degree 2 polynomial, and in the denominator, we have a degree 2 polynomial as well. So the rule is when the degree of the numerator is the same as the degree of the denominator, and we're taking a limit of our variable going to infinity, then it's going to, the limit is the ratio of the leading coefficients. So in this case, it's going to be 1 over 1, because I have a 1s squared on top, I have a 1s squared on the bottom. So our initial value here is that f of 0 is equal to 1. Right, now I can look at the steady state value of f using Final Value Theorem. So f steady state is going to be the limit as s goes to 0 of s times f of s. So that's the limit as s goes to 0 of, and for going to 0, I want to use the factored form. So I can just copy it from above. So that was s squared plus 3s plus 4 over, and then I have s plus 1 on the bottom, squared. All right, so that is s of s, s times f of s. I've already incorporated that s into it from when I was checking the poles of the system. All right, now looking at this, s going to 0 does not make the denominator 0. I'm not dividing by 0, so that's not going to be a problem here. So I can simply make s equal to 0 and do the limit. So on the numerator, I have 0 plus 0, and then I have a 4. And in the denominator here, I have 0 plus 1 squared, or just 1 squared. So the limit as s goes to 0 will be 4, and that is f steady state. So given enough time, the function is going to have a value of 4, and initially, it's going to have a value of 1. This doesn't tell us what happens between those two times, but we know at least kind of the bookends of the values of f.